So today we're going to be talking about dimensional analysis again, going in deeper into some aspects. And at the end of class, if you stay past 11:50, I am going to go over the double integral from the homework just as a review of how to do double integrals. Okay, so dimensional analysis. On Wednesday, we talked about dimensional analysis. We talked about those dimensionless groups like the Reynolds number or the Froude number that popped up in the example we did. And we said that those groups represent ratios of forces and they allow us to see how systems work even as you scale them up and down. And today we're going to show sort of specifically how you can use that principle to solve important, meaningful problems. So, for example, last class we non-dimensionalized this equation, right? And we got this equation. What this says is that we have three dimensionless parameters, right? We've got z star, t star, and the Froude number, and we know that z star is some function of those other two parameters. In this case, we know what this equation is, but sometimes it is possible to figure out what dimensionless parameters govern the behavior of a system without actually knowing what the relevant equation is. And this can be really useful, and we will see how. Okay, so we're going to call those dimensionless groups, those dimensionless parameters, pi's. Okay, so capital pi is pi. What is happening? Okay, so if a process is described by n pi's, then we know that pi1 is some function of the other pi's. This is pretty obvious, but what does this tell us? Okay, how can we use this? Well, let's take this car for an example. We are interested in something. In this case, we're interested in the drag force on this car. Why would we be interested in knowing what the drag force on a car would be? Thoughts?
It could help you save mileage.
Yes, the lower the drag force is, the better your mileage will be, because that means the less force you need to generate in order to go forward and push against all of that air that is pushing back on your car. So we are very interested in knowing what the drag force on a car is.
Increases speed also.
Well, the drag force, we know that the drag force depends on the speed of the car. We also know it depends on the shape of the car and its sort of general size. So we're going to use the length of the car as the characteristic length scale. So we pick a length scale that just sort of says, in general, this is the size of the car. Its speed, which is the speed of the car and the speed of the air around the car relative to each other are the same. And the density and viscosity of the air around it, okay, because the density and the viscosity of a fluid is going to influence how much drag it creates as you're trying to go through it. The actual relationship, though, is really complicated. It depends on this really complicated shape that's going to shape the air around it in all kind of ways. Okay, you might have to, in order to analytically with an equation figure out what the drag force on this was, you might have to find some expression and integrate it over the whole shape of the car. An easier way to do it is to find the two pi's, the two dimensionless groups that are relevant to this situation. And we'll talk about how to do that in this. We'll talk about how we find the pi's in the second. But what you end up getting is these guys. The second one should look familiar. What's that second one?
The Reynolds number.
Yeah, so this is the Reynolds number. And here we have drag force over rho v squared L squared. Okay. So this tells us that, okay, so these are the two relevant pi's that go into some equation, though we don't know what that equation is exactly. So now we make ourselves a little car. The little car is the same shape as the big car, but little. Okay, same shape, different size. Pi 1 is some function of pi 2. So if the Reynolds number around the little car is the same as the Reynolds number around the big car, so let's say I'm going to use small and big. If Reynolds number small is equal to Reynolds number big, what does that tell us? Does anyone have an idea?
Does that mean that the drag force is proportional to its size or weight or something?
So you're in the right direction. You're in the right direction. Pi 1, the drag forces are proportional, but the way they're proportional is a little bit more complicated. But how we figure out that proportion is, so pi 1 is some function of pi 2. So that means that if pi 2 for both cars is the same, then pi 1 is also the same for both cars, right? Because it's just like if you have y as some function of x, if you plug in x equals 2, you get out the same y. Same deal. So if pi 2, which was the Reynolds number, is the same for both of these cars, then that other pi, which had the drag force in it, also has to be the same. Did we write down the two pi's? Did people do that? Okay. So I'm going to call this CD for drag coefficient. Sometimes people will put a little 1/2 in for drag coefficient, like right down there. So sometimes you'll see it defined that way. In this case, the way we're doing this, it doesn't matter. So we'll just do it like this. Okay. All right. And this is how wind tunnels work. Okay. So in a wind tunnel, most of the time, you don't put in the full size version of whatever the thing is. Sometimes with a car, but especially with like a plane, like you'd need a really big wind tunnel for a plane to put a full size plane in. Instead, you want a little model plane. Okay. And so what we can do then is we put the little model plane or rocket or car or whatever in the wind tunnel, and we blow the wind past it. And then what can we measure in the wind tunnel?
The drag coefficient?
What we can measure in the wind tunnel is the drag force. Okay, because this thing is, this plane is on a little stick. You can measure the force on the stick. That'll be the drag force. And that allows you to calculate the drag coefficient if you want. But more importantly, you can then scale it up to get what the drag coefficient on the big vehicle would be. And so this allows us to figure out the drag coefficient on our big vehicle without having to actually solve these complicated equations, just with this relatively simple experiment. Okay. So This comes down to something called similarity, which we're going to talk about just because I want you to have heard this vocabulary before. So what similarity means is we want the prototype, the full-scale prototype of our vehicle and the little model one to be similar so that we can do this analysis. And there's different kinds of similarity. So geometric similarity means they're just the same shape, just scaled up or down. It means all of the different aspect ratios, basically, of these two cars will be the same. Then there's kinematic similarity, which means that at any point in the air around them, if you looked at the equivalent point, it'll be the same as this point over there, scaled by some factor. And then there's dynamic similarity, which is the same thing, but it's forces now. So if I looked at if I could somehow measure the forces everywhere in the flow, they would be the same in the big one and the small one, but scaled by some factor. Okay? So if they are dynamically similar, then we can do this analysis. As I said on this, I mostly just want you to have heard that vocabulary, okay, and to be sort of familiar with it. Okay, so if all the pies are the same, they are fully similar, and you can take measurements on the little model and then scale it up to the big one. Okay. Just as a reminder, when I say this, the shape is the same but scaled up, we could actually think of this as being like lots and lots and lots of different pies. Like there's a pie of this height over this length and the height of the tire over the height of the window, blah, blah, blah. It's just a whole bunch of different aspect ratios makes them the same shape. Just saying you can think of it like that. Now let's do an actual problem. So we want to predict the drag force on a car when that car is driving 50 miles per hour. So we build a 1/5 scale model, put it in a wind tunnel, and the first thing we need to figure out is what velocity should we have the air in the wind tunnel be? Okay? We want to pick a velocity to make the model similar to the big car. Give you a second to think about that. So how are we gonna pick the right velocity? How do you think? I'm gonna call on a random person, so I'm giving you a second to think about it. Joseph Tolley. Hello there, Joseph.
Hi.
Hi. So how do you think, so remember what similar means. Similar means that if all the pies are the same, then there's a similar. So how do you think we are going to pick the velocity for this wind tunnel to make the cars similar?
I'm thinking it'll be 1/5 of the actual sports car.
Okay. So you're sort of skipping a step. You've got, okay, you're skipping a step here because it's not always obvious. Remember again, what we want is for all of those pi groups to be similar. Right? And we said, if the Reynolds number is the same around the little one and the big one, then they are similar. So actually what we want to do is we want to pick a velocity to make the Reynolds numbers the same. So I'm going to use B for big car and S for small car here. And I'm going to say Reynolds number big is equal to Reynolds number small. Okay, Reynolds number small. And the Reynolds number is rho V L over mu is equal to rho V L over mu. that rho and that mu, the density and the viscosity, that's the density and viscosity of what?
The air that's flowing around the
Air that's flowing around. So if we assume the same air around the big one and the small one, same air, same temperature, then those will just cancel out on both sides. Okay. And now I'm going to solve for V small. V small is equal to L big over L small times V big. So now, what velocity are we going to use for the air tunnel, wind tunnel?
(250 miles per hour).
I'm having problems hearing.
Sorry, 250 miles per hour.
250 miles per hour, right? It's going to be 5 over 1 because the big one is 5 times as big as the little one times 50 miles per hour is equal to 250 miles per hour. So that is why we go through this whole process and sort of, so the intuitive thing that your mind probably leaps to is the little car is 1/5 smaller, so make the velocity 1/5 the size. But by doing this, we realize that it's actually the opposite. Okay?
So in this situation, how did you know there was only 2 pi's?
Because that is what we already determined for the force around of fluid flowing around an object. We already determined that, and we will get to how we find the pi's and how many pi's there are in a second.
Okay, sweet, thank you.
But these 2 pi's are just always the ones we use for this situation, and it's so common, we just, yeah. Okay, so, cool. Now, then, so another way of saying this would be Vs is equal to 5 Vb. Next thing we do, okay. So now we're continuing on from that problem. We've got it in the wind tunnel. The air is going at 250 miles per hour, which that's actually a lot. It might start becoming compressible at that speed, in which case you have a problem, but whatever, we'll assume it's fine. And we do it and we measure the force on that car and find it's 20 pounds. So now we want to find the drag force on the full-size car. So what do we do now? What do we think the second step is? Or let's take Allie Schumann. Hi, Allie. What do you think we should do in order to find the drag force on the full-size car?
Well, if you are decreasing the size, but no,
Okay.
then I don't know, you probably have to, I'm not really sure actually.
All right. Okay. So remember that the reason we set the velocity at 250 miles per hour in this car is so that we could make the little car and the big car similar. Why did we want to make the little car and the big car similar? Do you know? Or what does similar mean?
Well, they'll have like the same, like it'll be the same flow and the same drag force, just scaled.
Okay, not the same drag force, but you're close. And if we make the Reynolds number the same between the little one and the big one, something else will be the same too.
The drag constant, CD.
Yeah, the drag constant that we defined, and which was drag force over rho, I believe it was V squared. Let me check.
V squared L squared.
V squared L squared. Yeah, that should make sense. Okay. So that's what's the same between both of them.
I have a quick question.
Yes.
So I thought in order for us to be able to assume that if the Reynolds numbers are the same, then the drag coefficients are the same, they had to be similar. But
Yeah.
it sounds like we're using that assumption to try to make them similar.
No, we made them, there's only 2 pi's here, right? There's only 2 pi's, so we know that if the pi 2 is the same, then pi 1 has to be the same. If there were 3 pi's,
Okay.
then if pi 2 and pi 3 were the same, then pi 1 would have to be the same. Because remember, pi 1 is some function of pi 2 here. Pi 2 is the only relevant variable here. So if we make pi 2 the same between both of them, then pi 1 has to be the same. So what we did in the last problem is that we made pi 2 the same. We chose things in order to make pi 2 be the same for both of them. And once we had made pi 2 be the same for both of them, what we did is we made them similar. And so once we made them similar, then we knew that pi 1 would be equal, right?
Okay, so that just assumes that the function is the same for both of them?
Yes, yes, and that's what similarity means.
Okay, but we're like using that fact that the function is the same to make them similar, even though they have to be similar for the function to be the same?
Remember, they're also geometrically similar, they're the same shape. And we already figured out, we know all of the factors that are relevant to this. We know this. We can do that just by doing some experiments to see if we change this, it'll change the drag force somehow. And then we can just figure out all the factors that are relevant, which were the shape, the length, the scale, the density and viscosity of the air, the velocity of it. We already figured out through experiments or something that those were the only things that mattered. And so from that, we were able to figure out that these were the only 2 pi groups, and it's, as I said, you know it's the same function because we already figured out that those were the only things that go into this, and physics still works the same on the big one and the small one. Okay.
All right, thanks.
What that function is. Sorry, did you say something? Okay, so now what we can do is we can figure out the force on the big car. Okay. So the ratio of the velocity of the big one to the velocity of the small one, what's that ratio?
Quick question. It's a little hard to tell what's a V and what's an S at that size.
Okay, that makes sense. I will use M for model instead of S. Maybe that will be easier to see. Okay. M. Okay, so then I just solved for the force on the big one, and I got velocity big over velocity model squared, length big over length model squared times the force on the model. What is the ratio of the velocity of the big one to the velocity of the small one? What's that?
1/5.
1/5. We just figured that out. The ratio of the length of the big one to the length of the small one. What's that?
5.
5. So for this particular situation, we just found out that the force on the big one is just the same as the force on the model, which in this case is 20 pounds. So in this particular situation, once we did it, once we scaled up, we realized that the force on the big one is the same as the force on the small one. So when we set the velocity in the wind tunnel so that the Reynolds numbers were equal, then we know that this is true and we can figure this out.
How was the length? I'm confused about the length and the velocities. On the last one, we determined that. Could you go back to the last slide?
Yes, I can. So the last one, I don't know why it's doing this. Okay, the last one. Okay, we said it was here's the last one. So we said it was a 1/5 scale model. Okay, it's a 1/5 scale model. So we know then that the model is, the big one is 5 times as big as the small one. And then we did this with the Reynolds numbers to figure out that the velocity needs to be, the velocity around the little one needs to be 5 times as big as the velocity.
Okay, I see now. I see.
All right. So, questions about this? Do we see why this would be useful?
I've got a question, Dr. Nickerson.
Yes, Connor.
So how did we figure out what pies we were using?
Okay, so that's what we're going to talk about next.
Perfect, thank you.
Okay, we just started with this because this is one of the most common ways to do this analysis. Okay, like this is just done over and over again, all over. But next thing we're going to do is figure out what pies to use. Finding pies.
I had a quick question.
Yes.
So the first one that we used, the first pi, we set the Reynolds numbers so that they were equal. We adjusted the parameters so those were equal.
Mm-hmm.
What's the name of the second pi that we use in the next part?
So pies don't have to have a name, but this one is usually called the drag coefficient.
Okay.
And
So
if you look up drag coefficient in a book, sometimes they put 1/2 on the bottom. And the reason why is because of sort of thinking of it as a ratio between things, but the 1/2 would cancel out. So anyway.
Sure. So I guess my question is if we were able to find would we have done it in the other direction where we set them so that the drag coefficients are the same and then find the Reynolds number?
We could do that, but yeah, we could. There just wouldn't be a lot of a reason to do that because then the drag force on the big one is the thing we're interested in. We're not particularly interested in
the Reynolds number.
The velocity of the big one should be in order to, our end point is that we don't, what should the velocities be to make it similar?
Sure. Okay. But the pies are related through the function. So if you found one, you could scale and get to the other.
Yep. So we could call the one I call 2, you could call that 1 and the other one 2. It's arbitrary.
Okay. Makes sense.
Okay. Finding pies. So we know the parameters describing a system. I was saying that earlier. So we know the drag force is some function of L, V, rho, and U, but we don't know what function. And it's probably this huge, nasty one that's impossible to solve. Okay, so we don't know the functional form, but we do know that these are the important ones, and we can figure that out by sort of playing around with it and experimenting. So now we want to find some pies. And we can do this with any situation, but we're going to use this one with the cars. And the procedure I am going to teach you right now is called the method of repeating variables. This isn't the only method. You could also do this by sort of thinking about what kind of forces are in there, like the viscous force and the inertial force, like we were talking about before, and thinking, oh, there's probably ratios of those. Anyway, this method is going to be very useful. So first we list all of the parameters, which were drag force, rho, density and viscosity of our fluid, velocity, and length. That's our parameters. Okay, so n is going to equal the total number. So what's n?
5.
5. N is 5. So now we're going to list the primary dimensions for each of those n parameters. This is just like we did on Wednesday when we non-dimensionalized the equation. So I'm going to start with the drag force. What are the primary dimensions of that? Let's say Connor Barlow, you asked a question a little bit ago. So now can you tell me what the primary dimension of drag force is?
It's kilograms over meters or over mass times by time squared.
Okay. So mass isn't at the bottom. Remember that force is mass times acceleration, right?
Right, you are.
That will be mass times what is acceleration?
Meters per length per time squared.
Length per time squared. So m is going to mean mass instead of meters for this. All right, so that's force. Density. What is primary dimensions for density?
Mass per length cubed.
Mass per length cubed. Viscosity. Mass per length time. You should have done this in your homework. If you ever forget what it is, you can always just go from viscosity is Pascal seconds and go from there. You can figure it out if you need to. Velocity, length per time, and length is length. Okay. So how many? We're going to guess what's called the reduction, which is J. Okay. And our first guess will be J is equal to the number of primary dimensions. So how many primary dimensions are there in this system?
3.
3. Okay. So I'm going to guess J is equal to 3. Why is it called the reduction? Because the expected number of pi's, we're going to call that K, is equal to n minus J. So in this case, K would be 5 minus 3 is equal to 2. Okay, so we're going to guess that we need 2 pi's. Sometimes you won't be able to find 2 pi's that cover everything you need to cover. And so then you'll have to say, okay, maybe J is 2 and there's 3 pi's. Okay. Okay. So we're going to choose J repeated parameters. Remember, J was 3. And we're going to make the pi's out of those 3 repeating parameters. So of those parameters we mentioned at the beginning, we're going to pick 3 of them, and we're going to use those to make our pi's. So we're not going to use the dependent variable. The dependent variable is the thing we care about. So in this case, with the cars, we already talked about the thing that we care about that we're trying to find. What was that?
Drag coefficient.
Not the drag coefficient. I'm talking about
Drag force.
Drag force. Okay, so drag coefficient is something you can find on the way to drag force, which is what you care about. So we're not going to use the drag force. Okay, I'm going to remember that our parameters were drag force, density and viscosity, velocity, and length. Okay. So we're not going to choose drag force. We want 3 parameters. These parameters have to cover all the primary dimensions in our problem. So we need mass and length and time to be somewhere in those parameters. You're never going to pick something that's already dimensionless. Like sometimes you would have like beta. Beta is dimensionless. You'd never pick that. Basically, that would be a pi. And we want to pick ones that, so for example, if you had like length and area, if we had some problem where diameter and area were two of the things, then we wouldn't choose those, both of those, okay? Pick constants over variables and pick simple parameters over complex parameters. So now we are going to pick 3 of these guys in order to use to make our pies out of. And when we're talking about fluids, the most common ones people choose is a D or a L for like a length scale, a velocity, and then a mass or a density to give us mass. So in this case, let's choose density, velocity, and length, and these will be our 3 repeating parameters. And one reason, the viscosity is the other one we could have picked. And if we did pick it, we could still do the rest of this and we would still end up with pies that work, but just the viscosity has mass and length and time in it. So it's just a little bit simpler to do these ones that are just, each of them only has 1 or 2 dimensions in it. So remember, we chose rho V L. And now we're going to generate K pies. Does anyone remember what K equaled?
2.
Okay. Okay. So we're going to take one of the remaining parameters and then we're going to non-dimensionalize it with the repeating parameters. This is just like we non-dimensionalize those variables when we non-dimensionalize the equation on Wednesday. So let's pick, and then you repeat. So yeah, and then you can repeat that. So let's do this. The 2 ones that we cared about were, so we picked rho, V, and L as our repeating parameters. So what were the 2 parameters that are left over?
Drag force.
Mass and
What? Okay, Peter, I think you said something?
Drag force and viscosity.
Yeah, drag force and viscosity. So pi 1, that's the one we care about. So that's the one I'm going to put drag force in. And then pi 2, I'll put viscosity in. Okay, I'm trying to non-dimensionalize drag force. So I think it's helpful to write out the parameters right here. So this is m L over t squared. And I want to non-dimensionalize this with those parameters. So first things first, I got to get rid of that mass, right? So how do I get rid of the mass?
What's the density?
density? Yeah.
And the density. Okay. So that'll be mass over length cubed. See, and this is why it's nice to get repeating parameters that only one of them has mass in it. It's nice, it makes it easier. What do you think will be the easiest to get rid of next?
T.
Time.
Time, right? Because time is only in velocity. So if we get rid of time, then only length will be left over. So how do we get rid of time here?
Divide it by velocity squared.
Divide it by velocity squared, because when we do that, it'll be length squared over time squared down here. And those will cancel. Okay, and so now if I put this all together, that becomes length to the 4th over length squared becomes length squared. So now I just got to get rid of a length squared. How do I do that?
Divide by length squared.
Divide by length squared. Okay. Just gonna say times 1 over length squared. Okay, all right. So I've done that. And now I'm going to do the same thing with viscosity. So remember, viscosity was mass over length time. So let's do the same thing. First, let's get rid of mass. How do we get rid of the mass?
Density.
Divide by density. Okay. Now we should probably get rid of the time, just like we did before. So how do we get rid of that time?
Multiply by velocity.
So if we multiply by the velocity,
Oh,
it will be
yeah,
like
yeah.
this, like length over time. So those won't cancel. So divide by the viscosity. But that's why I write it out here, to make sure I've done it right. So I divide by the velocity, I mean. So times L over T, which means boom, boom. Okay. And that leaves me with L squared over L. That leaves me with 1L. So how do I get rid of that 1L?
Divide by length.
Divide by length. Length squared, 1 over length squared. All right. And then once I've done this, I can realize that this is 1 over the Reynolds number. And then most of the time I would go ahead and flip it around just to make it the more familiar one. And so I just make it rho v L over mu. Another thing though is, since we know that the Reynolds number is very common, so if you have a situation in which you know that inertial forces and viscous forces are important, and you know that we have rho and v and mu and a length in here, you can guess that one of them is going to be Reynolds number, and you'll usually be right. Okay. So then we check that all of our pi's are dimensionless, and we check that we have enough of them. And how do we know we have enough of them? Well, we know that all 5 parameters are here. So we've used all of them. We've used the drag force and the viscosity and everything. We know that they're all dimensionless, and we know that these 2 are not dependent, are independent. So you can't get pi 1 just by taking pi 2 and squaring it or multiplying it by 2 or whatever. So since it covers everything and they're all dimensionless, we know that we have enough pi's. If we weren't able to do that, we would have to reduce j by 1, which would mean we need another pi. And so then we'd try to find the 3 pi's and so on. In this case, 2 pi's covers everything.
Hey, Dr. Nickerson?
Yes.
Oh, sorry, go ahead.
I just was wondering, like, when would we have to reduce, like, are we going to have to reduce it, or is it usually, or is it always a guess?
It's always a guess at first. So you just have to try it and see if you can figure out k number of pi's that, as I said, you'll know is enough pi's if all of your parameters are in there and they're both independent. You can't get one of them from the other one. That's how you'll know you have enough. And if you can't do that with just the number of pi's you have, you'll have to add another pi and then repeat.
Okay, thank you.
Okay, I was wondering if it's okay if you don't have enough like constants, you can use a variable. So like, for example, if rho might change in the problem or v might change, but you can still use them, right?
Yep. And in fact, rho, so velocity changes, and sometimes even rho and viscosity change. In fact, in this case, I said try not to use variables, but we used velocity instead of viscosity, even though velocity is a variable. So it's not a fast rule, it's just kind of a suggestion.
Okay.
And then
I also had a question. How do you know that you can just flip the Reynolds number?
so you can always flip it. These are ratios, and all we care about is if something is imagine something is a function of 1 over x, right? Then it's also a function of, y is some function of x. Then you can also say y is some function of 1 over x. And they're the same. Let's say y is equal to 2x. Then that also means y is equal to 2 times 1 over x. Remember, we don't care about the actual form of the function. All we care about is that these are the parameters that are in it. And so flipping it over doesn't matter. And it needs to be dimensionless, but if you flip it over, still dimensionless. And these are not the only pies that would work, right? So you could pick viscosity, velocity, and length as your 3 parameters, and you would end up with 2 different pies, but they would still work for this. You would still be able to scale up from one to the other. These relationships would still be the same. And the reason why is because what's governing the behavior here is the ratios of all these things, which is bigger and which is smaller. And that is why this is useful, because we can do all of this useful analysis without necessarily stuff like that mattering. Yes, so short answer is you can just always flip 1 over. And if you want to, not only can you flip it over, you could multiply it by whatever, multiply it by 5. Doesn't matter. This will still work. Because then when you set them equal to each other, 5s will cancel out and everything will be the same.
Can you remind me again how we found the specific set of parameters at the beginning? Did we just know them, or?
We knew them, and how you would find that is experiments. So you just sort of try a bunch of different things, like turn a lot of knobs and see what changes it. Or you could sort of think through logically what would be involved. Various ways that we could get a set of parameters, right? And if when we did our experiments, we couldn't get this to work, that might be a sign that we had missed one of the important parameters.
Okay.
In this class, I'll usually just give you a set of parameters. I'll say, we know that blah, 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 blah are important, but that's how we would know.
Okay. Thank you.
All right. Any other questions on this? Before, as I said, then I'm going to go over the double integral from the homework.
Did you go over how to tell if we need to go back and reduce J?
So as I said, we had the 5 parameters here. So we had force, drag, rho, mu, v, and L. And we want all 5 of these to be in our pies somewhere. Okay. So force, drag, density, viscosity, velocity, length, they're all in either one or both of them. And we want them to be, as I said, independent, which means you couldn't take pi 2 and just square it or multiply it by something or flip it over and get pi 1. And if you cover both those things, you can have it. There is an example in your book where you have to reduce it. I think that's probably the best way to understand that. So I forget where that example is. I believe it. Okay, I think example 7.7, you have to change it. So, yep. Yeah, example 7.7 in your book, reduction in a soap bubble. Go over that one because that's one where they start out with n equals 3. And so they start out with thinking that they're going to have just 1 pi and then they have to have 2. So I believe. If I remember
Okay,
correctly,
thank
that's
you.
what it is. But go through that example, and I think that's the best way to understand that. All righty. So this is another one where I had a lot of writing on this, so I'm going to save my writing and post that. Now let's go over that integral in the next 9 minutes before my next class. Peter, are you trying to ask a question? I sound like a robot.
Oh, sorry.
But yeah, were you trying to ask a question?
Nope.
Okay. So this is your homework problem. I feel okay with just going over it because as I said in the homework, this is a common example. And if you search, you can find how to do it. So once you non-dimensionalize the differential equation, you should have gotten dz star over dt star is equal to -1 over the Froude number squared, where z star is equal to z over z naught, and t star is equal to v naught over z naught t. Now we're going to integrate, and this is just me. You should have all learned how to do double integrals at some point, but it might have been a while ago. So I think I want to do a refresher. And what I'm going to do first is I'm going to figure out what boundary conditions we're going to use, because the boundary conditions are what's going to allow us to find the constants of integration. We're going to integrate twice. So that means 2 constants. Integrate once, you get C1. Integrate twice, you get C2. And so we want 2 boundary conditions. Okay, so let's think about where we know something. And at t is equal to 0, we know that z is equal to z naught. That's what z naught means. Just the initial z. And so when t is equal to 0, t star will be 0, right? So that means that at t star is equal to 0, z star will equal z naught over z naught will be 1. So that's our first boundary condition. At t star equals 0, z star equals 1. I'm going to just write that out. Okay. Now our second boundary condition is that the other thing we know is that t equals 0, v is equal to v naught. And so at t star is equal to 0, dz star dt star is equal to 1. And how I knew that was, well, first of all, I just know that this is going to be the non-dimensionalized velocity, dz dt. And so it'll work out this way, but I can prove that it will work out this way by saying d z over z naught over for z over d okay. of z star, z naught z tar over d of z naught over v naught t star. This is squared like that. Okay. And I could pull this out. It's equal to v. Okay, so I just said dz dt is equal to v. Pulling this guy out, we get z naught v naught at z naught v naught over z naught. Okay, so v naught times dz star dt star is equal to v. So that means that dz star dt star is equal to v over v naught. Anyway, so when v is equal to v naught, that just means that dz star dt star is equal to 1. That is all of that meant. Okay, so I've got my two boundary conditions. Now I'm going to integrate. So what I'm going to do, sorry, it's like that. So first I'm going to rewrite this differential equation as d dt star of dz star dt star. All I'm saying there is that the second derivative is just the derivative of the first derivative. That's all that means. Is equal to -1 over fruit number squared. Why it helps to write this out is otherwise you will be tempted to just put this dt squared over on the other side, but that will not work out for you. Okay, so now we separate and integrate. Okay, now I'm going to integrate both sides. D of dz dt, you integrate, it just becomes dz dt. Just like if you integrated dy, it would become y equal to -1 over fruit number squared dt, or not dt, sorry, t star plus c1. And I know that at t star is equal to 0, dz star dt star is equal to 1. So that means that c1 is equal to 1. Okay, so now I have dz star is equal to -1 over the fruit number squared t star plus 1 dt star. Integrate again. I get z star is equal to -1 over 2 fruit number squared t star squared plus t star plus c. And how do I know what c is? I know that at t star is equal to 0, z star is equal to 1. So c, oh, that's c2. c2 is equal to 1. And so we end up with d star is equal to -1 over 2 fruit number squared t star squared plus t star plus 1, which is the same equation we found in class when we started from the top and then non-dimensionalized it. All right, that was that. Just wanted to do this review of how to do double integrals. My next class is starting now. So I will see the rest of you on Monday. You can come to my office hours at 2 if you have any questions about anything. Connor, what were you saying?
No, I was waving.
Oh,
Thank
you were
you.
waving? Okay, wave, hi.
Thank you. See ya.
Dr. Nickerson, could you just show the entire thing all at once?